real quick is do a sample problem and show you how to deal with these decay problems. A lot of them will be pretty standard. This oscillator has these properties. It's not damped. Just go use the equations and some physical intuition. But there's one kind that I think is a little confusing, one kind of problem that relies you really understanding exponential functions. So I thought I'd do one of those. So let's look at an example of an exponential decay problem. All right, there we go. And the idea that I'm trying to get you to understand is you don't need the details often. Need the details. Okay. So let's say, here's the problem. Let's say, I don't know how to specify this as the problem. There's a star. An oscillator with mass is 2 kilograms. All right, hilarious. And constant and B is 0.01 kilograms per second. And the question is something that sounds like you don't know enough, right? How long to lose 1/2 of the amplitude? Okay. You don't know the amplitude. You don't know the mass. You don't know how this thing got started. You don't even know that it's a mass on a spring. It could be a pendulum, for all you know. You know nothing, right? But you can still solve the problem. That's the amazing thing, is you can still solve the problem. Because we can describe the amplitude as A equals A naught e to the minus bm b over 2mt, right? Oh, yeah, you have with the mass. Yeah, you have to have the mass. Yeah. You don't have the spring constant. You don't have the length, is what I meant. If it was a spring or a pendulum, you don't have some properties. So what we can do is just say, well, we know that it decays like this. And you got to know a little bit about exponential decay. If we're plotting the amplitude now, and this is time, then at time equals 0, that's when you have your maximum, A naught. Okay. Just plug 0 into that equation. E to the 0 is what? 1, right? So that's when A equals A naught. So this is what exponential function decays look like, except they look more like a real one. Like that. Oh, wow, that's perfect. Frame it. So the question then is, when does it get to halfway down? Well, I don't know the amplitude, but I know what half the amplitude looks like. It looks like that. So we're really just asking for when does this happen? Okay. T star, you could call it, or T half, the half-life, or whatever you want to say. So really, you just need to know how this thing curves down. You don't need all the details of the motion if it's an exponential problem like this. So what you would want to say is when, how long to lose amplitude, lose half amplitude. So I'd say, when does that happen? So it's kind of like in kinematics. When we ask when something happened, we made the something happen mathematically, and we called it T star. And we just solved for T star. So it's that kind of a thing. So we have the amplitude as a function of time. When does it equal A naught over 2? When does that happen? Well, say, okay, A naught over 2 equals A naught e to the minus b over 2m t star. You know, this is the special time when it equals A naught over 2, not just the whenever it is a function. And then mathematically, that you can deal with, maybe. Get rid of the A naughts. Hey, we don't need the amplitude. Look, it goes away. When you're asked for a fraction of the amplitude, you put it on both sides of the equation and it's gone. Then you're left with 1/2 equals e to the minus b over 2m t star. So you just solve that for T star. Right? Oh, we can do it. I know we can do it. So how do you get rid of an exponential in an equation? Yes, you take the natural log of both sides. Wow. You guys are so expressive. Ooh. Did y'all learn to say lawn? You didn't? Okay. So it's cool. You don't have to say natural log, you say lawn. So I was raised to say lawn. So you take the ln of both sides. So the ln of e to the minus b over 2m t star is just minus b over 2m t star. The natural log of 1/2 equals minus b over 2m t star. Right? And now if you are exponentially inexperienced, and by that I don't mean it's gotten a lot worse, I just mean you haven't done a lot of exponents, you're going to panic and think, oh, I'm going to get a negative number, oh no. Oh, but if you're exponentially experienced, you say, oh, look at that. Boom, negative gone. Right? The ln of a negative, you flip it over or something like that. I think that works. And you do all this, and you plug in numbers, and you can get a number. Right? We're down to just numbers now. We were given b, we were given 2m. I know the natural log of 2 because I have a calculator. And you get 277 seconds. Right? So there you go. So you solved it without having the details. So I just want to make sure if you need to be a little bit familiar with how these exponential functions work. Okay? And then you can also do detailed problems. You could solve for the amplitude at any time t, or whatever. Now you're thinking, is this important in my life? And the answer is it is. This is the reason for something that impacts you a lot. Well, maybe not you, but your forebears. Is if this thing decayed this fast, how did these clocks dominate technology for 270 years? Right? Clearly they have to be driven. But how do you drive it and have it go at the right frequency? Because actually if you drive a motion, it goes at the frequency you drive it at. It doesn't go at the natural frequency. So this is the kind of thing that does it. This is the escapement. So you can see this is the pendulum going back and forth here. And this is what Huygens invented, right, that made it work. This is the pendulum going back and forth here at its own frequency. And this is the thing that you wind up, or that has the two big masses on it, like at your grandparents' house. You pull it this way, and then it slowly pulls it back. Or with springs. And this thing is just wound and ready to go, but you can see it's applying a force. I can't time it. Now. Right? It's like pushing it on that side and pushing it on this side. But it doesn't push until this decides it's time to get there. Right? So this thing, the pendulum, is still setting the timing of the motion. And this is the thing, though, that's giving it a little kick to keep it going. This is what they'll tell you is happening at the Houston Museum of Natural Science with the Foucault pendulum. Okay? This is the big thing. This is the reason clocks tick. Is this mechanism, right? Do you hear this thing ticking? Shh. No, it's not ticking because it's not being driven. It's not stopping. This is the reason clocks tick, which is a huge impact on society and culture and all this stuff. So TikTok was like the robot, and those are the robots, of course. I love Kesha. I'm sorry. I am pretty sure that Kesha is a misunderstood genius. I'm serious. She is definitely a misunderstood genius, and I don't think she's going to get anywhere because she's too misunderstood. But I'm quite certain that she is a genius for many, many reasons.